Hello and welcome to Toddcast number 55. They are definitely going fast. This one kind of a mid-chapter sort of catch our breath, organize, and then look at the big picture. So we've thrown a bunch of reactions at you really, really quickly, but they've all fallen into this category of oxidation reduction. So I want to do some summary of oxidation reduction reactions, toss in the nuances of different reactions, and just get it organized into one page. So it's not exactly a spider chart because unlike a spider chart where we usually start with one thing and show all the things we can make, this is more of a going back and forth. You want to be able to go from a carbonyl to an alcohol through reduction, and also be able to go from an alcohol to carbonyl through oxidation. And so it'll be the back and forth process. But also, I've mentioned this concept of a protecting group. So we're going to elaborate on that a little bit. And in doing so, the reactions we're going to summarize right now can be used in synthesis. And then protecting groups are, they're born out of issues with synthesis. So I want to go ahead and start with just an overall chart. It looks really daunting and overwhelming at first, but this is kind of what we've been doing. So just let me remember, if I can, some of the reactions. I think we oxidized, lost a bond to H and gained a bond to O, went from primary alcohol to an aldehyde. And we used different reagents, but if you recall, we used, in particular, PCC, known as pyridinium chlorochromate. You can also hear it called Collins reagent in some textbooks. I'm not really big on the names, although I probably should be because you never know where you'll hear about it in the future. But I'm going to call it just a poisoned oxidation, where you poison the reaction so that it stops at the aldehyde. You get rid of you add pyridine, get rid of water, and it stops. If you do not add pyridine, you do it in water, it can actually go to the aldehyde, and the aldehyde can then oxidize to the carboxylic acid. So we have this process of going from primary alcohol up to an aldehyde, up to a carboxylic acid. The aldehyde, as we just learned, can also undergo a Grignard reduction, meaning I go from 2 bonds O to just 1 bond to O by adding an R group. A secondary alcohol can undergo oxidation up to a ketone. It can lose this H and gain a bond to this O for 2 bonds to O. It can also undergo a Grignard reduction and go to a tertiary alcohol. And so it's kind of seeing this big picture, knowing your reactions go in the forward direction and reverse direction. And so filling it in chart style hopefully will help in that synthesis concept. So if we do some reaction, like make an alkene, the alkene we turn into a primary alcohol through BH3 addition to a terminal alkene. And then we work our way through, maybe we make an aldehyde, which turns into a Grignard, which we do something to make a ketone. Just knowing how to zip along this chart will be helpful. So a few things I want to point out. Primary alcohols have 2 H's to lose. So here's one, here's the other. So oxidation involves loss of H and gain of O. So we think about it in that sense. If you lose a bond to H and gain a bond to O, there's 1 H to lose, and that accounts for the process of going from a secondary alcohol, a primary alcohol, to an aldehyde. So we lose one of these H's, but because there's still an H on carbon, and I'm going to call it so-called oxophilic carbon, the one that wants to gain or has a love for oxygen, we can lose that other H and turn it into an OH. So I can lose this bond to H and gain a bond to O on that carbon. So the oxidation state, if I remember how I do it, I get a plus for the bond to oxygen. Terrible looking plus, let me redo that. I get a plus for the bond to oxygen, a minus for each of the bonds to H, and a 0 for the carbon to carbon bond. So it's -1, 0 plus plus minus. So now it's a +1, and then a 0 plus plus and plus for +3. So every time I lose an H and gain a bond to O, oxidation state goes up from -1 to +1, +1 to +3. It changes by 2 electrons every time you lose an H and gain an O. And I should say more specifically, lose a bond to H, gain a bond to O. Okay, so I have this oxidation process. When it gains a bond to carbon, you aren't doing both. You're losing a bond to O, but you're gaining a bond to carbon, and carbon is a break-even situation. So oxidation state only changes by 1. So I have a 0 and 0. I have a minus for that one, and a plus for that, which adds up to a 0. So it gets reduced. And then when I go from here to here, I have a 0, 0, plus and a plus, or +2. So these are full oxidations where you lose 2 electrons. Grignards are reductions by only 1 electron. So if this is a +2, I'm predicting that this, when it gets reduced via a Grignard reaction, should go down to a +1. Let's double check. Plus for each, or sorry, 0 for each bond to an R group. So overall then, sure enough, +1. Okay, so the redox table is working. I know how the reactions kick in. It is important that you go ahead and list the various reagents. We can do this, but let's just do one more thing. So there's H's. So we oxidize first to an aldehyde, then to a carboxylic acid. Secondary alcohol only has 1 H, so it only has 1 oxidation process to do. And then the tertiary has absolutely no H's to lose. So tertiary alcohols are the ending point. We can't really oxidize because we don't have an H to lose from that carbon. So because losing an H is imperative to the oxidation process, you have to have an H on the oxophilic carbon in order to have oxidation. Okay, so what reagents are going to do this? Oxidizing agents, things that are rich in O, poor in H, CrO3, can take the primary alcohol all the way to the carboxylic acid, secondary alcohol all the way to the ketone. KMNO4, when cold, can take it all the way to the carboxylic acid, it being a primary alcohol, secondary can go up. Note that if you use pyridine, as mentioned before, you can stop it. Reducing agents, for going backwards, lithium hydride can take anything across. So lithium hydride can do acid back to primary alcohol, it can do aldehyde to primary alcohol, it can do ketone to primary alcohol. Sodium borohydride can only do aldehyde back to primary alcohol, ketone back to secondary alcohol. So it's probably important to maybe I'll number these. I'll say reaction 1, 2, 3 for oxidations, and I will do a different color. Maybe I'll do reaction A, B, and C. And note that this can only do B and C, or this can do A, B, and C. And then this can do 1, 2, 3, 1, 2, 3. But with pyridine added, it can only do 1 and 3. It cannot go all the way up to the carboxylic acid. Okay, and then one more thing to add in there, Grignard reduction. I did MGBR before. If you want, you can also make this a chloride as mentioned. So I'm going to say that. Second step, you treat it with mild acid workup. So it's up to you to also note the other conditions. But the key thing, the hydrides, reducing agents, carry out the reductions. Grignard carries out the reductive addition of a carbon. Oxygen-rich compounds carry out oxidation of alcohols up to carbonyls, and carbonyls to extreme carbonyls, like carboxylic acids. So it isn't that this is an overwhelming amount of information in one sitting. We've had it over a few lectures, so hopefully it's starting to get into place. But when you look at the big picture of this, there's a lot going on here. So make sure you know the reactions forward and backwards, know your reagents. You can survive on just these 5. I may add a reagent or 2 during class. Don't stress about it, just add it. There's room to add another one here, room to add another one here. Not really room to add another one here, so I'm got to be pretty much done with those. So onward we go. Just want to see how we can deal with a question like this. Which of the following compounds will not react with Jones reagent? It's like, ah, dang it. I have no idea what Jones reagent is. And this is going to happen. So like just this previous slide, I mentioned Collins reagent is the one with the pyridinium chlorochromate, PCC. So occasionally people throw a name at you. Not sure what it is, but I at least want to take a look at what the compounds are. Primary alcohol has 2 H's that it can lose. Secondary has 1 H you can lose. Aldehyde has 1 H you can lose. Ketones have no H's to lose. So the first 3 can all be oxidized. The ketone cannot. As far as reduction goes, this has 1 bond to O, so can't lose that. 1 bond to O, can't lose that. But an aldehyde and ketone have 2 bonds to O, so they can be reduced. So I just want to summarize what this can be. So again, primary alcohol can be oxidized because it has H's to lose, but it has only 1 bond to O, so it cannot be reduced easily. The reagents we've been talking about so far. Secondary alcohol has an H to lose, but also cannot be reduced, at least not on the reagents we've used. Aldehyde has an H to lose, so it can be oxidized, but it has a double bond O, so it can also be reduced. And the ketone said has no H's to lose. It's 2 R groups on the carbonyl, but it can be reduced. So if I look at it this way, if I'm looking for the one of these things is not like the other, it's right there. I have two of these and two of these, so can't be a reduction process. So Jones reagent must be some sort of oxidation. So it says which ones can, except for. So in other words, all of them can do it except for one. That's exactly what this is. So this is more test logic when you don't know all the facts. It is perfectly fine to use that. It's actually a really powerful tool. If you start thinking this way, solving problems with only 40, 50, 60% of the information, not ideal, but certainly a skill that will help you in life. So you can still deduce D because it's one of the things not like the other, but Jones reagent is CO3 and H2SO4. It's an oxidizing agent. Notice the absence of pyridine. So Collins reagent is this when you get rid of H2SO4 and you use pyridine in conjunction with HCl, another strong acid. But in this case, we use H2SO4, sulfuric acid, in aqueous conditions with CO3. Okay, so primary alcohols can be oxidized into carboxylic acids. Secondary alcohols can be oxidized into ketones. Aldehydes can be oxidized into carboxylic acids, but ketones cannot be oxidized, so the best answer, choice D. So we did learn, however, that oxidizing a ketone, we could do it if we added a peroxy acid, that Beer-Villager reaction we talked about earlier. So that's why I had to be cautious when I was saying not easily or not readily or not oxidizable or reducible based on the reagents we've done so far. But the reality is, if you want to do a reaction, you're going to find a way to do it. Chemists live by that motto, so to speak. So we can oxidize a ketone under much more rigorous conditions using a peroxy acid. But in the conditions we just summarized, ketones are essentially inert. Okay, so that summarizes the oxidation reduction reactions we're going to do for this chapter. We're going to add more as we go, but get organized in that so you can answer questions like this. Oxidation of a primary alcohol into an aldehyde involves. So I know stopping at aldehyde means I'm only going to oxidize one of the two H's on the primary alcohol carbon. So to do that, I know I need to use Collins reagent or PCC, pyridinium chlorochromate. So pyridine is my magic ingredient. So that gets a great big T for true. It does, in fact, gain a bond to oxygen because oxidation is a gain of bond to oxygen at the oxyphilic carbon. That's just a generally true statement about oxidation of any kind. It does result in an increase in oxidation state by 2. The 2 is extra information. But I don't know about a chiral center, so let's go ahead and draw this out. So there's my reaction, my pyridinium chlorochromate concoction, my Collins reagent. So 2 identical H's, sp2 in the end. So you have no chiral center in the beginning, so you don't lose one. You're going from achiral to achiral. So for this one, pyridine does prevent it, so A is in fact true. It is an oxidation at this oxophilic. The carbon with an oxygen is oxophilic, gains bond to O. B is true. The oxidation state went from -1 to +1. So let me just double check that. I get a plus for that bond, 0, minus, and minus. Minus, minus, plus, and 0. So it is in fact -1. Here we have a 0, a minus, a plus, and a plus. So +1, so it did in fact go up by 2 electrons, making that a true statement, but loss of the chiral center did not happen. Okay, so I'm in a happy place when it comes to oxidation. So it's time to start focusing on synthesis. That's going to be the ultimate application of pretty much all of the reactions we've been doing so far to date. So one of the things that, again, we have to worry about is if we have a molecule, it has multiple functional groups. Case in point here, we have an ester at one end and a primary alcohol at the other terminal end. So if I want to react with this ester, but I'm worried about this OH, for instance, if I do any reaction where I make this OH a better leaving group, so let's say protonate here, have something come in and kick the ester out, I can have an intramolecular reaction where this attacks in, forms a 1, 2, 3, 4, 5-membered ring. Ultimately, when the electron pair kicks back out, it kick that. So go from an ester to a lactone, an internal ester. I don't want to have that happen. Let's say I want to do something with the ester and I do not want that reaction to occur, and I need to protect it. So if I want to treat this with a Grignard reagent, for instance, Grignard reagent I'd hope would attack here, come in, kick it out. Problem with doing that reaction is that Grignard is also a strong base. It will deprotonate that H, make this O minus come in, kick out the OET, and you'll never see Grignard adding. So it first deprotonates it, that can close on itself. So to avoid that problem, we have to do something a little different. First, we add something that the O will react with. Oxygen is really good at binding to sulfur, as we learned, to phosphorus, to boron. It's also really good to forming a bond to silicon. So if you believe sand exists, you believe then silicon can go on. So when I do this, I get oxygen now bound to trimethylsilane, TMS. Okay, so feeling pretty good about this. I can now do the Grignard reaction, which no worries, there's nothing to deprotonate here, so it's going to go on. It's going to attack twice because it's an ester with a leaving group, so I want to make note of this having to have two equivalents. We add one here and one here. And then now all I got to do is take that silicon off. Random fact, if you happen to know this, fluorine is used to etch glass. So it can, you put patterns on there, you put it like a sub-protective coating, you treat it with a fluoride-based component, and it'll eat up the glass, then you peel the thing away and you have this cool little etched glass arrangement. That notion that fluoride can interact with glass means fluorine must have a high affinity for silicon. So this silicon right here with the 3 methyls and the oxygen now, treated with HF, you take it off, and you now can go to the compound you wanted. So my hope was to add 2 of these to the ester end, and now I was able to do it. I protected the OH, carried out the reaction with the other part of the molecule, and took the protecting group off. So this is my protecting group on, so this is now protected. And this removes it, so this is now deprotected. So it's pretty straightforward. And I definitely will put some sort of synthesis in your future that will involve the need of a protecting group. And so your dead giveaway of that is when you see 2 functional groups on the same molecule, which is pretty common, you have to start worrying about what I protect. So you protect when you have 2 reactive groups where one is more reactive than the other. So in this case, because OH was more reactive with the Grignard because it took advantage of its base-like nature to be deprotonated, that means it reacted with the wrong group. I wanted to react with the ester, it reacted with the OH. So if I protect the OH, it leaves just the isolated ester to react. Everything's fine. So it's not just because I had 2 functional groups on the molecule, but it's because I had a 2 functional group situation where the reagent I'm adding prefers the one I don't want to react as opposed to the one I do want to react. Okay, we can also protect carbonyls. This one I mentioned briefly before, something called a ketal. I need to use a more general term. Ketals come from ketones, acetals come from aldehydes. And so because I'm going to use an aldehyde this time, rather than an ketone, I'm going to protect it as what's known as an acetal. And I'll write that out when the time comes. But let's say I want to carry out this reaction. I'm going to carry out something where I react with this alcohol, let's say oxidize it up. My worry is that if I oxidize here, I run the risk of oxidizing my aldehyde. Or if I treat something with PBr3, I run the risk of possibly reacting with here. Whatever it might be, there's an outside chance if I try to react with this alcohol, I'm going to impact the aldehyde. So one of the best things you can do early on is keep track of your atoms. So I'm going to say, here's my O. Here's my O. They're here and here. Here's the rest of it. It's a vicinal, they're neighbors. So vicinal diol. The remaining atoms are the O that used to be there, an H and an H. Guess what 2 H's and an O make? H2O. So that's where your water comes off. As a teacher years ago heard speak, she would say, Bart Simpson will protect your carbonyls. So I don't know if you know who Bart Simpson is, but I think that's one of those TV shows that never goes away and everybody sort of knows it. But if I protect this aldehyde as this, then I'm free to react with the alcohols any way I want. So note that it has to be done with an acid. And bases do not form or break acetals or ketals. And the reason I think that is actually really good information to know is because our stomach and our lysosomes are acidic because we have a tendency to break down starches, and starch linkages ends up, they're known as acetal linkages, if you've heard that word before. When one sugar residue is connected to another, connected to another, connected to another, it has the same functional group, meaning acidic conditions can form it and break it. So we hydrolyze our linkages in the presence of acidic conditions. Okay, on to this one. So here I have this lactone or internal ester, cyclic ester, and here I have a ketone. So I want to react at the ester, but I do not want to react at the ketone. So I can add the same protecting group. I've drawn it different this time, but it's the exact same thing. There are sp3 carbons in both these spots, so it's free to rotate around. Just decided to draw it differently, just to be different, no other reason. So let me see where this one's going to go. There's that part. And I know it's going to be this O right here with these two H's, so I know my water. So there you go. Here's my O and O, and here's my H2O. We're set. It is now protected, so now we can react with this. And then the same molecule, if I were to use NADH4. So just point of interest, let's say I want to react with just the ester and not the ketone, then I would protect the ketone and be good with the ester. But we only protect when we need to. So if I, instead of reacting with the ester, let's say I only want to react with the ketone, again, because of this resonance contributor right here, this only has a small delta plus. This carbon has a much bigger delta plus, meaning the ketone carbon is much more reactive than the ester carbon. So if I were to use lithium aluminum hydride, it reacts with everything. So reactive, it can react with the weaker ester and the ketone. But if you recall, sodium borohydride only reacts with ketones and aldehydes. So I can selectively reduce here without affecting the ester. So in this case, I didn't need to protect anything because I was aiming for the more reactive site. So I choose a reagent that barely reacts with one and doesn't react with the other to get the result I want. So our strategies are, look at the various sites and decide which one is more reactive. If you want to react with the one that's more reactive, then choose a reagent that barely gets it done. If you want to choose with the one that's less reactive, then protect the one that's more reactive, and then expose or react with the one you have left over. So this is the protecting prep work. To take these off, ends up you just do the opposite of what you did to put it on. Acidic water will take these protecting groups back off. So H plus and more water, H plus and more water, H plus and water. So in the forward direction, I want to have it anhydrous. I just want to have the diol and the acid. In the reverse direction, for the last one, I apologize. We didn't protect it, so why am I doing that? So H plus and water to take this off. H plus and water to take this off. So if I have very little water, it goes forward. If I add water, it goes backwards. So it's a very easy group to put on and take off. Again, we always want to use mild acid to prevent other reactions. So the motto in chemistry, barely get things done. Scoot by. Take the lowest possible route you can so you don't get side products. Okay, so a lot of information was thrown at you in a very, very short span of time. Protecting groups, that concept, and summary of a bunch of reactions. So now I'm going to try to fuse it all together. I'm going to try to synthesize it into specific questions. So here's my overall synthesis. I'm going to go from something that has a methyl ketone on one end, a primary alcohol on the other, and I want to add an ethyl group to the end with the alcohol while not touching that group there. So a couple ways I could try to do it. My first thought is maybe I could use 2-carbon like acetylene, deprotonated intact, but OH is not a very good leaving group. It will just get deprotonated. I could turn this into a Br, add the acetylene, but then I don't have a functional group there to work with. So it ends up, it's not necessarily a good plan. So instead of trying the acetylene approach, add 2 carbons, I'm going to try the Grignard approach. Grignard's going to react with a ketone and not the alcohol. So I have to do a couple things. Number one, I need to protect because I have 2 functional groups, and this one is the one that's going to react more readily. So if I do a Grignard, I need to make sure that's protected. So my to-do, my non-sequential list, I must add 2 carbons, check. I must prep this group up and turn it into something that can receive a 2-carbon Grignard reagent. I must protect this group, and then if I protect, I always have to deprotect. So I'm going to add 2 carbons, and I'm going to choose the Grignard as opposed to acetylene as a nucleophile. I have to lose an H because right now I have 2 H's here. And in the end, I only have 1 H. So losing an H, if you recall, is oxidation. So if I lose an H, I'm going to turn the primary alcohol into an aldehyde. I must protect the ketone, and then in the end, I must deprotect to regenerate the ketone. So deprotect the ketal and turn it back into a ketone. Note that I mentioned this is non-sequential. You got to know what you're going to do. So I'm looking at the overall changes, add a 2-carbon species, get that carbon in a position to react with a Grignard, which means oxidize it up to a carbonyl, an aldehyde in this case, and protect and deprotect. Well, I'll tell you the easiest thing, protection is always first, deprotection is always last. So those two, no problem. So the question is, do I have to get it ready for the Grignard before I add the Grignard, or do I add the Grignard first? Hopefully it's kind of a no-brainer. You have to turn it into something that will react with the Grignard and then do the Grignard. So in sequential order, we'll have the following. Protect first. So there's my protection of the ketone into a ketal. Second step, have to oxidize it up to a functional group that can react accordingly. So there's my aldehyde. Third on the list was add the Grignard. So 2-carbon Grignard, MgBr with an ethyl group. And then last but not least, deprotect. Again, deprotection requires weak acid so it doesn't overreact with water. So let me get rid of my 1, 2, 3, 4 because we now have made them sequential. And now just a matter of what reagents we use. So if you recall, protecting the ketone requires a vicinal diol. So first step, vicinal diol in the presence of acid and no water. Second step, I want to stop it at the aldehyde, so I use PCC, pyridinium chlorochromate, Collins reagent. I'm going to then add a Grignard in this step, so the CH2, CH3 with an MgBr has to come in. So I made, I think, a potential mistake, and I need you to help me out. I can't remember if we had an issue before with the Grignard and the alcohol. I think, wasn't that why we had to protect in the previous question? If we have an alcohol, Grignard is a strong base and can simply deprotonate the ethanol. The problem when you deprotonate the ethanol, you end up with ethane, the deprotonated form, and a lot of heat. That equals fire. So if you do this, lab just caught fire. So absolutely imperative that I use an aprotic solvent that cannot protonate the Grignard reagent. Absolutely positively imperative. So this must be done dry. So for anybody going on to the next semester of chem where you're going to do Grignard reagent in lab, you'll know you do it in this weird concoction where you have a rubber septum on your flask, and you have to insert things by syringe so you do not get any moist air, anything from the environment in there. So you want to have a dry environment, and you want to make sure everything you add is anhydrous, free of any water. Okay. So last but not least, deprotect. Like I mentioned before, a weak acid like in protonate amine ammonium in water will be just barely strong enough to protonate this without causing an E1 elimination. So just want to throw one question, see how this went. Under what circumstances should a molecule be protected when carrying out a Grignard reaction? So why did we just have to do this? So was it because the reactant has a protic hydrogen at a site where activity is desired? Nope. That was where we had our alcohol where we want to have to react. We want to get rid of it and turn it into a carbonyl so it can react with a Grignard. So that's prepping the molecule, converting the primary alcohol into an aldehyde or a secondary alcohol into a ketone. That's key. That's what we want for this, not for protecting it, but to make it reactive. When the reactant is an aprotic carbonyl that has only one functional group, well, this is a lot of words that mean nothing. Key thing here is one functional group. If you only have one functional group, you don't have to protect anything. It's when you have multiple functional groups. When the molecule has a hydroxyl group rather than a carbonyl group, again, same story. You want to not necessarily protect it because you have one group or the other. That's where you have to react and turn the hydroxyl into a carbonyl. That's why we oxidized it. You protect when you have multiple functional groups, and you want to react at one site and not the other. So protect the one that you do not want to have a reaction at. So I didn't want to have it react at the carbonyl. I wanted to react at the other site. So I protected my carbonyl and then converted the other site to what I needed, an aldehyde, carried out my reduction, and then deprotected, got the carbonyl back. So you protect when you have multiple functional groups where you only want one of the two to react, and you have the risk of both of them reacting, or the one you don't want to have react. So the key word here, multiple functional groups. A lot of information thrown at you. This protecting concept can be really tricky at first, and it adds a whole new layer to synthesis. So before, we just worried about what reactions you do in the sequential pathway to get from one to the other. Now we have to consider reactions and not reactions, if that makes sense. So if we have two sites, we want one to react and another one not to react. You have to pick your reagents carefully, or you have to protect your more sensitive functional groups. So when there are two or more and you don't want to have one of them react, you have to consider protecting it. Lots and lots and lots of information on this one. So this is one of those where it's worth going back and redrawing that chart for yourself. Don't just copy it from there. Try to make it from scratch, and keep in mind the number of H's on the carbon that contains an OH, or the so-called oxyphilic carbon. Tells you how many times it can be oxidized. Know your reagents. Again, we keep on mentioning, or I keep on mentioning, sodium borohydride only does aldehydes and ketones. Lithium hydride reduces everything. Grignard can reduce a carbonyl if there's no leaving group, as in a ketone or an aldehyde. It adds once through addition and you get an alcohol. If it has a leaving group like an ester, it will add twice and you end up with a tertiary alcohol in that case. And then just seeing the overall big picture of these processes and protecting groups. So lots of information. Thank you for sitting through this, and just a couple more to go in this chapter. I just accidentally went and showed you what the next thing is, but it's going to be all this little bit closer look at the mechanisms behind how we make those protecting groups. So see you at the next podcast. Thanks for listening. Bye.